Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is BirdNET, a deep learning solution for avian diversity monitoring. Let's get started. Despite what some conspiracy theorists may say, birds are all around us. They show up in nearly every ecological niche. What's more, the presence and diversity of birds can be an important indicator of an ecosystem's health. So, scientists use monitoring of bird populations as a means of keeping tabs on the environment. For a long time, though, this meant that researchers had to go out in the field and look and listen for birds. They'd then tally up a count of what birds they saw and where. This obviously has a lot of limitations as a method. You need a lot of people, there might be bias in how the data is collected, and you can't get round-the-clock observations. More recently, scientists have turned to passive acoustic monitoring. By placing microphones in locations of interest, researchers can collect a rich data set of bird calls and other sounds. This is a cost-effective way to do large-scale ecological monitoring that can be as accurate as having humans in the field. But what do you do with all those hours of recordings? Using humans to sort through it all is obviously too time-consuming. So in this paper, researchers built an artificial neural network that can take in audio clips and provide a label for the bird species present in them. The type of network they use is a convolutional neural network, which is a really well-known technique for solving computer vision problems. But they're using bird calls, not pictures. So how does a method meant for images help here? Well, any auditory signal can be turned into an image by creating a spectrogram. This is a plot of the frequencies present in a sound and their intensity over time. By turning the audio clips of bird calls into a spectrogram, the researchers can pass them through the convolutional neural network architecture represented here, and then read out the network's guess at the final layer. Of course, for this model to be good at its job, it needs to be trained on labeled bird calls. And for that, they need a large collection of data. To get a large collection of labeled bird calls for training, the researchers turned to the enthusiastic community of citizen scientists who have uploaded files to the Xenocanto website. They augmented this with more calls from the Macaulay Library of Natural Sounds and ended up with over 250,000 audio clips representing 984 species of birds. To be able to feed these audio clips into the network, they cut all the clips into 3-second snippets. To mimic the challenge of identifying birds in the wild, they also mix audio from up to 3 different species together. Given this dataset, the network is trained to output the probability of each of the 984 bird species in response to a given clip. For clips longer than 3 seconds, the probability for each 3-second snippet are averaged together. Species given high probability are treated as the network's labels for that audio clip. Once trained, we can see how well the network does. Is it able to accurately identify the species in a clip? If we look at audio clips that are very similar to the kind that the model was trained on, the model does pretty well. It has a mean average precision of 0.791, meaning that 80% of the time the model says a species is present, it really is present. But if we test the model on different and more realistic audio settings, performance decreases. Specifically, the authors collected 12 days worth of audio from a set of recording devices in the Sapsucker Woods Sanctuary. While the training data was made of clips with well-isolated sound, this real-world audio data contains challenges like background noise and birds at multiple different distances from the microphone. And the model struggles with that, achieving an F-score of only 0.414. The F-score is a combination of precision and recall and reflects the overall ability of the model to identify all species correctly. Finally, the researchers check if this model can do exactly what they built it for: monitor bird population diversity over time. For this, they pull 4 years of historical recordings and compare the model's bird counts to the counts of their own expert field researchers over that same time period. What they see is that there are some bird species for which the alignment between the model and the ground truth is pretty good, but for other species, the model is not doing well. The authors speculate these results might be biased by the fact that the recording device is near a feeder, which may cause certain species to be overrepresented in the dataset. Overall, the authors note that their model's performance, while imperfect, is competitive with other researchers who submitted to the Bird Clef Challenge, which uses the same real-world audio that they evaluated on. The authors also made BirdNET available for anyone to use online. So if you have any birds you need identified, go ahead and upload a clip. That's all for now. Remember to subscribe to this channel if you'd like to see more examples of how machine learning and AI can be used to understand and protect our planet.